Hello everyone, this is Dr. Lennon, and today we'll be going over sections 8.1, angle measurement, and 8.2, perimeter and area of some select polygons. So let's first start by talking about 8.1. So 8.1 talks about angle measurement. So angle is a pretty naive concept. I'm sure most of you are familiar with it, but an angle is the size of an opening between two intersecting lines. So there's a few ways to measure this. When you get into trigonometry, you can talk about radians and stuff like that. But in this course, we'll mostly be talking about degrees. So these we'll say are typically measured in degrees. And degrees you can kind of think about as being parts of a circle. So kind of we're subdividing. So kind of like the big one is a circle has measure 360 degrees. So if you look at the circle and you had the center and we looked at where the radius is over here, if you go all the way around, that measures 360 degrees. So you can start talking about parts of a circle if you want. So just proportionally, we could say a half circle has measure 180 degrees. And what that's going to be is essentially that's going to be just a straight line. So if you have a straight angle, that would have measure 180 degrees. And you can subdivide this for any constant that you would want to look at. For instance, if you wanted to do a ninth of a circle, that angle would have measure 40 degrees. But the other one that is significant for us is a quarter circle. This is what's known as a right angle, so this will be very important in the coming sections. So if you look at what a quarter circle would look like, so these aren't always in the context of a circle, but that's denoted with a little box like this. So if you have two lines that meet and there is a box drawn like this, that means that those meet at a right angle. So this has measure 90 degrees. So the kind of big payoff for that is going to be the Pythagorean theorem for triangles that we'll learn about. So that, we'll look at that in section 8.3. Okay, so there are some names for some different types of angles here. So some terminology. So what is the terminology? So there are different names. So names for different types of angles. So the first of these we might talk about an acute angle. So if we talk about an acute angle, this means that the angle has measure less than 90 degrees. The dual notion of that is the obtuse angle. This has measure greater than 90 degrees. A right angle, as we saw above. So we talked about the next two above, but just to write it down on this list, a right angle has measure equal to 90 degrees. And for a straight angle, this has measure equal to 180 degrees. So there are some theorems from geometry that allow us to look at these different types of sets and kind of identify measures of missing angles. So we'll hit the high points on those. So let's talk about some different types of angles. So kind of let's talk. Let's say relationships between angles, and there are many different types of angles that we can talk about relationships between, but we'll just be kind of hitting the high points on the ones that we encounter most frequently. So the first of these are vertical angles. So this is a pair of angles. So these are opposite angles for intersecting lines. So that's what vertical angles are, and these angles have the same measure. So for example here, just one quick example, if you had two lines right here and they intersected, and let's say this angle happened to have measure 85 degrees, and we wanted to know the measure of this angle right here. Let's say it were x, then we would say angle x. So sometimes they use a little angle to denote what angle we're labeling. This must have measure 85 degrees also. So this 85 degree angle and x are said to be vertical angles because they're on opposite parts of those two intersecting lines. So they have to have the same measure. So another thing that comes up is the interior angles of a triangle. So this relationship can actually be expanded to all polygons, but for now let's just focus on the triangle. So for these, the sum of the angles of a triangle So if you add all the angles inside a triangle together, that has to add up to 180 degrees. So a quick example there. So if you had, say, I don't know, some triangle. So let's say this were, 40 degrees here and 80 degrees up here, and we wanted to figure out, let's say this is angle Y. What is the measure of angle Y? Well, basically 40 degrees plus 80 degrees plus Y, all three of these angles have to add up to 180 degrees. So we can use that to go ahead and solve for Y. So we get 120 degrees plus Y equals 180 degrees. And then we could subtract 120 from both sides and we get the value of Y. So Y is going to be 60 degrees. So that's how you would use the sum of the interior angles. And then the last type of thing for relationships of angles are what's known as basically parallel lines cut by a transversal. So basically what happens here is, in this case, corresponding angles must be equal. So what does an example look like? Well, parallel lines mean, right, they never intersect. So if you had two parallel lines, maybe that'd look like this. So these lines are parallel, they never intersect. And then you have a transversal, so that just means a line that cuts across both of them. Then your corresponding angles are going to be equal. So let's say this is angle A, and this is angle X, and maybe this is angle, let's say B, and this is angle Y. Then what would we have? Well, they're in the same part of so angle A would be equal to angle X, and angle B would be equal to angle Y, because those are corresponding angles, meaning they're in the same part with respect to the transversal and the parallel line for each line. So angle A with respect to the top parallel line is in the same position as angle X with respect to the bottom parallel line. And the same is true for B and Y. And then you can get more angles equal to each other from looking at vertical angles as well. So we'll look at a couple examples. Okay, so let's go ahead and look at an example where for each of these we're just going to solve for the missing angles. So let's look at this example where we have, again, these are not necessarily drawn to scale. I'm kind of drawing them just freehand, so we'll see. So this top angle right here is 143, and then we have angle A right here, angle B, and angle C. So first thing to note, so angle C equals 143 degrees by vertical angles. Okay, so we know angle A, so we know the top angle and angle C, so now we just need to find A and B. Now there's two ways to do this. You can look at A and the 143 degrees on top, or C and B, but basically you just need to recognize that there's two ways to see a straight angle, and a straight angle has to have measured 180 degrees. So let's say angle A plus 143 degrees has to equal 180 degrees by straight angle. So that's the measure of a straight angle. And then what we can do is we can just subtract 143 on both sides. Sometimes we'll write the degree symbol, sometimes we won't if we're being a little bit lazy. But same with the angle symbol. This leaves us with angle A, and that adds up to 37 degrees. So we know angle A is 37 degrees, so basically we have angle C, we have angle A now, and we can get angle B because angle B is a vertical angle with angle A, so we also know that angle B has to equal 37 degrees, and this is by vertical angles. So let's look at another example here. Let's look at example B. So this one is another just straight angle example, nothing too crazy. So let's say we have some angle here, and this one is 104 degrees, and we want to find the measure of angle X. So we know 104 plus X has to equal 180 by, again, the fact that they form a straight angle. So we can just subtract 104 from both sides. So we get X has to be equal to 76 degrees. And that is all we need to do for that problem right there. Okay, let's look at C. So C involves a triangle. So let's say we have this triangle right here. So we have, actually let me draw that a little bit better because this one is supposed to have two of the same angles here. So we have So these are both supposed to have measure A, the base angles, and the top angle we have as having measure 48 degrees. So if the top angle has measure 48 degrees, again, we know A plus 48. If you add all three angles, they have to add up to 180 degrees. So basically that tells me 2A plus 48 has to equal 180. And then I can subtract 48 and divide by 2. So I know 2A is equal to 132. And then I divide by 2. So we get A is equal to 66 degrees. So both of those base angles have measure 66. All right, so one last example from this section. Let's look at D. What do we have here? We've got, so let's say we've got the parallel line situation with the transversal. We can label quite a few angles here. Let's say this one is 65 degrees. Oh, and then we can do a whole bunch. Let's say A, B, C, D, E, F, and G. Let's just go ahead and do all of those angles. So we've got 7 angles we can label. Well, the first one, let's figure out A. So we know A plus 65 has to equal 180 by the straight angle measurement. So subtract 65 on both sides, and we get A is equal to 115. Okay, so now we have the top two angles. So basically, we can figure out D and E from corresponding angles. So angle D corresponds to angle A. Angle E corresponds to 65. So we know D has to equal 115. It has to be the same as A. And E has to equal 65 degrees by corresponding angles. So we have those two now. And then we can get B and C from vertical angles. So angle A has to equal angle C, and angle B has to equal 65. So we get B equals 65 degrees. And C has to equal what A was, which is 115 degrees. So again, we have these two now from vertical angles. And then F and G are going to correspond to B and C. So angle F will have the same measure as angle B, and angle G will have the same measure as angle G. So F will equal 65 degrees, and G will equal 115 degrees. And this is again by corresponding to angle B and angle C. All right, so that's it for section 8.1. So let's go ahead now and move on to section 8.2. And again, these examples that we looked at are going to be similar to what we see on the homework. So let's go on to 8.2. So this is section 8.2 is perimeter and area of quadrilaterals. We'll look at some area of other figures in 8.3, mainly circles and triangles, but for areas today, in this section we stick to quadrilaterals. So the first thing that we want to talk about is the perimeter. So the perimeter of a figure is an easy concept. So the perimeter of a polygon is the sum of the lengths of its sides. Okay, so that's pretty straightforward. So we can look at maybe some examples. Basically, we're just trying to find sides and add them together. Nothing too tricky there. So they can write down formulas for very special cases, but really you don't need to know any formulas for perimeter. You just add the sides around the figure. So we could say find the perimeter. So maybe we have a trapezoid where the top has measure 20, and then we have 28 over here, 36 over here, and the bottom is 43. So for this one, the perimeter is just all four of those sides added together. I don't have any measurements here, but they could be in meters or inches or feet, and your answer would just be in whatever that unit happens to be. So we just add all the way around the sides. 20 plus 28 plus 36 plus 43, and that should come out to, I think, 127. So 127. Let me double check that. I just did that mentally, but I don't want to get it wrong since I'm recording it. Yeah, 127. All right, so B, what about if we look at, what about something like a rectangle? A rectangle is pretty easy. So rectangle, that's all that means is that's a four-sided figure where all of the vertices are 90-degree angles. So maybe I say this side is 8 and this side is 15. Well, basically on a rectangle, the opposite sides have to have the same measure. So basically the perimeter here, we would have 8 plus 8 plus 15 plus 15. So this would come out to 46. So sometimes they do write down a formula for the perimeter of a rectangle. So if you have a rectangle in general that has, say, length L and width W, and it happens to be a rectangle like this, then the perimeter, the general perimeter formula is sometimes given as twice the length plus twice the width, 2L plus 2W. And if you notice, that's what we did up above. Basically, we just doubled 8 and added it to twice 15. So that's the perimeter of a rectangle. And, we could have ones that are maybe a little bit more interesting. Oops, sorry about that. So let me get the old eraser. So what could be more interesting? Well, let's look at this example, part C. Maybe we have a figure like this. So it kind of looks like an L, an upside down L at least. So all of these are right angles essentially. But I don't give you all the sides. In fact, what sides do I give you? I say, okay, well this side right here, this side has length 18, and this side on top has measure 11. So how am I going to figure out the perimeter of this entire figure? Well, the point is, if you look at kind of this piece X and this piece Y, we know that X plus Y has to add up to 11 because that goes all the way across the top. And then if you looked, so if Y was this piece and X was this piece, and then maybe we call this piece right here A, and then the piece on top B, well then we know A plus B has to add to the vertical measurement, which is 18. So basically the perimeter of this entire geometric figure, the perimeter here, so if we kind of, the perimeter here is going to be still just 18 plus 11 plus 18 plus 11, which is 36 plus 22, which is 58. So, I mean, although it looks more complicated, the point is the x plus y still has to add to the top length of 11, and the a plus b, the vertical components, still have to add to the 18. So really, although this figure is isn't a regular looking polygon, it still kind of behaves the same pattern as the rectangles. Okay, so let's look at areas. So let's look at a few different areas here. So there's a couple formulas, but really nothing too crazy. So, and again, we're just looking at quadrilaterals, so areas of quadrilaterals. So what are the areas of the quadrilaterals? Well, basically the the first one, the square, rectangle, and even the parallelogram all follow the same convention. So the area for all three of these figures is just base times height. So base times height. So nothing too complicated there. Parallelogram just means you have two sets of parallel sides. So it just needs to be configured so that you know the actual height. The one that's a little bit trickier for the four-sided figures is the trapezoid. So what is a trapezoid? Well, a trapezoid just has one pair of parallel sides. So this figure would be a trapezoid if the top side were parallel to the bottom side here. So basically what you have to know is you have to know the vertical height, which is typically not going to be one of the two sides because these are both kind of slanted, and then we would label both of these the two bases. So if you label both of those base 1 and base 2, then the formula for your area here of the trapezoid is given by base 1 plus base 2 divided by 2 times our height. And the way I kind of like to remember that is I imagine, well, if you could somehow smush this trapezoid into a rectangle, then the average base length would be the average of your two bases, which is basically what you do. If you add B1 and B2 and divide by 2, you're basically taking the average of the two bases. So let's look at an example where we find some areas. And again, the units of the area, what we want to remember there is if you have a measurement for the side lengths, the area is really measuring the square units on the inside. So your area units are going to be square units, not just regular units. So for instance, if you were measuring a rectangle in feet, then the area measurement, the units of the area, would be feet squared. So for this example, we just want to find the area of the polygon. So let's say we have something like this. So this is a rectangle. Again, I don't have like a protractor handy, so these aren't the neatest polygons in the world, but get the idea. So 7.5. So if I make two marks like that, those are inches, and on the bottom 21.6 inches as well. So this is a rectangle, so my area formula is just going to be base times height. So my area here is 21.6 times 17.5. So that comes out to so 378 exactly. So I would say 378, and then normally I would denote it like this, inches squared. Sometimes in alternative notation, sometimes you might see people write 378, and they might write SQ period IN period. So both of them mean the same thing. They both mean square inches. B, maybe let's look at a trapezoid. So maybe we have a trapezoid. Again, these things with these trapezoids is you can kind of draw them both ways. So it doesn't have to be that the parallel sides are necessarily the top and the bottom. They could be going in the other direction as well. So in this case, this side is parallel to this side. So the parallel sides are always what you want to think of as your bases. So we have 36 meters, 39 meters here, and then our bases are 36 meters here and 21 meters here. So the area of this trapezoid one thing here, this is the right angle, so that makes this 36 meters right here my height as well. So usually if they give you both sides and both of them are slanted, meaning this isn't a right angle, one of them would have to be, they would additionally have to give you the height, or next section we could use the Pythagorean theorem to figure it out. But in this section, one of the sides will typically be the height, or it will be labeled with a height. So the area formula here is base 1 plus base 2 over 2. So that's going to be 36 plus 21 divided by 2. So this I'm thinking of as my base 1, and this I'm thinking of as my base 2, and this guy right here, the 36 on top, I'm thinking of as my height. So, and then I need to multiply that by my height of 36. So you can do that in your calculator. And I get 1026. And again, the units were meters, so this would be meters squared. That's typically how I write it, or we could use the alternative notation SQ period meters period. So either one of those would work. Okay, so that's it for the basic area formulas, angle measures, and finding areas of polygons. Again, the homework questions are not too difficult for these two sections, so we will pick up next time going over 8.3 and 8.4, where we get into some special formulas with triangles and circles. So this is Dr. Lennon signing off, and I will talk to you next time.